learned to always, at the Balkans at least, smell the water. Okay. Yeah. So let's get started. I also, just like Rob, made my presentation in SwiftUI. We can play a bit with that. So my presentation is actually about, make a little smaller, is about SwiftUI and build systems and how they're the same thing. And so there will be, the SwiftUI bit is sort of more the second bit of the talk, yeah. Also, during the talks, I sometimes wanted to throw that blue ball that we got. If you feel like throwing the blue ball at any time during the presentation, do it. Like, I love that. The blue ball that we got, if you didn't leave it in your hotel room, so go for it. Yeah, so when I think about build systems, when I started, makefiles were the build system, right? Like, that's the first thing that comes to mind when you think about build systems. And here we have one rule of a makefile. And we have a target, a colon, and then the dependencies. On the next line, very important, is a tab character, and then the command. If you don't write the tab, it breaks. And so this is a way to express how to build something, and then specifically how to build this target. So let's scroll to the next slide. And so here we're going to build one.html. That is the target we're trying to build here. And we can specify our dependency, which is one.md. And you can see now in the graph on the right that we created a dependency, right? So one.md is a dependency of one.html, which means that if we request one.html anytime one.md changes, it needs to regenerate a new one.html. To do this, we use command mark, so we take one.md, run that through command mark, and put it into one.html. And this is all you need to create a simple build system, right? We can make this a little bit more generic because what I'm actually trying to build here is a static site generator, and this is just a makefile to build my static site. So to make it a little bit more generic, let's say we have 2.md. So we wouldn't want to duplicate this rule, but actually make it generic, and so we can replace the destination here with $@. I know it's a bit hard to read if you're not into makefiles. We can write less than, so it becomes very cryptic, right? And we can do the same thing where it says 1, we can replace that with a % in both cases. And now we can actually see that if we were to request 2.html, it's going to look for 2.md. And if we, of course, whatever name you come up with, this will work for all your files in your directory. Let's make it a little bit more interesting. So also build index.html. And index.html, actually, let's do something where it depends on both files. So we can say, actually, our dependencies are 1.md and 2.md, and now the dependency graph looks like this. And to build it, we're just going to concatenate it, yet another weird variable. Now, what I think is really interesting, and the reason why people write these makefiles is because it takes a long time to build something, right? Not this website, like this is super quick, but this is why people started writing makefiles. The first time you build something, it takes a while, but then you want to have incremental builds. If, let's say, 1.md changes, we want that to only rebuild 1.html and index.html, and we can see that here. It does not trigger a rebuild of 2.html. Likewise, if just 2.md changes, then of course, just those two files need to be regenerated. And so for a simple website like this, of course, it doesn't matter, but this is why people use makefiles, so that you get incrementalness. Let's look at the next example. It's a little tricky with the scrolling. Okay. This is something that's maybe already a little bit closer to home. Swift package descriptions, and we know this, right? Like, we write these, and these are incremental as well. So we can create a target shared with no dependencies. We can create a target for the server, and that actually depends on shared. We can create a target for our client, which also depends on shared. And so we're building up this graph already in our minds, right? And yesterday I was talking to someone where it took maybe a minute and a half to build the app, and they couldn't do packages yet. And this is why, like, packages can really help, because let's say we made a change to our app in one of the Swift files there, that actually will only rebuild the app target once you have a full build. If we were to change something in our client code, it changes the client, of course, it rebuilds that, and it rebuilds the app, and then we're done. And if we were to make a change in shared, we would probably need to rebuild everything. And so the Swift compiler, or the build system, actually takes this into account, right? Like, it's an incremental system where we actually give it some rules, and we say, well, server depends on shared, and so on, and it computes this graph on the right here, probably in a different representation, and it turns our description into an incremental system that's fast to rebuild. Swift actually also does it at the source file level. At the end of the presentation, there's a WWDC talk linked where they explain this way better. And even if we were to make a change, right? Like if we, for example, made sure that the app depends on both the client and the server, it's actually pretty smart about this. So if we were now to invalidate shared, it first builds shared, then it actually builds the server and the client, and then the app. And to us as humans, it's very easy to see that. As a compiler or as a build system, it's maybe a little bit harder. But all of that works exactly like we would expect, without us having to do too much thinking. Let's look at a simple spreadsheet. So a spreadsheet is also a build system. And so let's step through this. So we have a dough calculator. If you want to know more about dough, I'll refer to Daniel for that. There's a link for that in the final slide as well. This is a dough calculator, and with dough, you compute, for example, the water amount by taking the hydration level and multiplying it by the flour level. And then, of course, the total is the flour and the water added up. And so here we have a formula B1 times B2 for our water. That's hydration times flour. And so we can visualize this as well, right? So this water cell, that's cell B3, and so it depends on B1 and it depends on B2. So B3 depends on B1 and B2. If we look at the formula here for our total amount, we can see that's B4. I'm trying to not say B4 because that's confusing. So B4 depends on B2 and B3, and so we can add edges there as well. B4 depends on B2, and B4 depends on B3. And now we have a graph of our mental model of that spreadsheet. And if we were to change the hydration, for example, so cell B1, what it does, it recomputes that. So let's change it. Well, actually, before we look into how it recomputes, I just changed it, and now we need to recompute. And it used to be that in the first spreadsheet implementations, they would just recompute the cells left to right, top to bottom, until nothing changed anymore. They would just keep repeating that until nothing changed. And then at some point, they came up with a system like this, where it actually tracks the dependencies, it tracks the order, and made it an incremental system. Because now that we changed B1, that is invalid, and then it only needs to recompute B3, and it needs to recompute B4, so all the dependencies below. And note that it did not need to recompute B2, the flour amount, because that doesn't depend on it. Again, to us as humans, this is maybe very natural to compute in this order. To the computer, it's not always. And you could implement this in way less efficient ways. Changing the flour is interesting as well. So let's change it to 900. Now our cell B2 is invalid. And now we have a choice to make. Are we first going to compute B3 or are we going to compute B4? Again, for us humans, it's easy to see. You just start with B3, obviously, right? But it's not so easy. And if you're trying to ever implement an incremental system yourself, the keyword to search for is topological ordering. And so if you do the topological ordering, B3 is ordered before cell B4, and so that's why it runs B3 first. And so all of these things, in my mind, are the same. Makefile, Swift packages, the Swift compiler, spreadsheets, and now we're going to try to bring that knowledge to our iOS world. So here we have that same dough calculator, and we can interact with it. So we can change it, right? And it changes the values here. We can change this to 900, and everything changes. And now, how would you implement this on iOS, right? And so it used to be that we had UIKit. With UIKit, you would typically work with the model view controller paradigm, or some people call it model view presenter. The big problem with model view and controller is that your views need to stay in sync with your model. This is not easy. For a calculator like this, it's very simple, right? Like we can all write this, but it's really hard to do this at scale or in a larger team. You need to always take care. So first you build up your view tree, then you set the right values, and then anytime the model changes, you need to change your view, and vice versa. Anytime your view changes, you need to update your model. This is a hard problem, and people struggled with this. I struggled with this. Realizing that that problem exists is a big step forward, and as a community, we actually moved to model view model, MVVM. Not everybody did. I wasn't really a big user, but it's the step forward we took as a community, and it actually really helped. Because the view model, depending on your definition, is a class or a type that observes the model, has reactive streams or reactive processing to then have outputs that the view can connect to, so that everything always stays in sync. That's the thing MVVM solves, and it does so really well. So let's try to implement this with a view, MVVM. There's a lot of code on this slide, and you do not need to understand everything. We'll talk through it. I'm not a combine expert. That's the framework I used here. I'm not an MVVM expert. You could use RxSwift or Reactive Cocoa or anything else. Now, the first thing we have here is a hydration subject. And if you're not used to this, this is kind of like a state property in SwiftUI. So we create a node for that in our graph. Then we have a flower subject, same idea. Then we have our combine latest, and it combines the hydration in the flower into the water amount. So you can see combine latest, you could see the map that actually does the computation, the assignment. It's a lot of code, but you can get it to work. And then it's the same for combining the water and the flower into total weight. Let me zoom out a little bit. So we have some more space. We then take the water amount, put that into a view, and the same for the total. And actually, note that there's a lot of similarity to this spreadsheet example, right? The top part looks exactly the same. And I think that's very interesting. So we can run with this and change the hydration, and then of course it does what you would expect. I think you change the hydration, then the water gets computed, then the water stack and the total weight get computed, and the total stack get computed. What I don't like about reactive programming is that it's really hard. It's hard to know which operators to use. Do I use combine latest or zip or one of the other ones, and throttling and all of that? You need to think so much about these signals and about the events that happen. It's really hard for me to debug this stuff because I cannot step through it. And it's just so much code. And so then we can look at actually how SwiftUI solved this problem. So this code that we just saw here is just setting up all the publishers and everything, right? There's no view creation. So now let's compare that to SwiftUI. This is all the SwiftUI code to build all the observation, to make it incremental, and to build the view. So I think that's a big win. And let's also step through this so you don't have to parse everything at once. For both of these state properties, SwiftUI creates a node. So we have a node for hydration and a node for flower. Then there's the two computed properties. And for the computed properties, actually nothing happens in terms of the graph. The graph here on the right is actually the attribute graph, the underlying system that SwiftUI uses. And so the computed properties, we can access them in the body of our farm sample, but nothing gets created in the graph. And then SwiftUI actually runs the body, so it creates a form, it creates a section, it creates these two text fields, and the other views. Because we access the hydration property in our text field, SwiftUI creates an edge. So SwiftUI tracks exactly which state properties we access. And for every state property we access in the body of our view, it creates an edge. If we were not to access that state property, it would not create an edge in the graph. And what that means is that anytime hydration changes, we need to rerun the body of our view. These actually use the water and the total property, and they indirectly access it, so it creates another edge, but of course, in the end, there's just the one edge. So I summarized the rest of the views with the ellipsis. I hope you forgive me. And so let's look at what happens when we change the hydration to 0.62. The node invalidates, and actually SwiftUI will mark the body also as I need to re-execute this. And then it creates all those other views, and all is good. So far, no big expectations. But when I first realized this, that the state properties cause changes to the body of our views, I worried. Because what if you have a state property in your content view, right? At the very root, does that recompute everything all the way down? That would not be good. And so we can actually have a look at that. So we can create a nested struct here. And in the nested struct, we're going to add some text. Just a simple property, doesn't matter what it is. So this property is called text, and we're going to create a property for that in our nested struct. And now we're going to use that nested struct in the body of our form view. So it says hello world. And now let's step through the steps when we invalidate the hydration. So we invalidate it. It's dirty. It recomputes the body. It recomputes everything else that's summarized, so the form, the section, the text fields, the labeled content. And then it hits the nested struct. SwiftUI knows, and it can compare these values. It can see there was a nested struct with hello world before. There's a nested struct with hello world after. I do not need to recompute the body. And so it stops here. It does not recompute the body of nested. And this is the incremental bit that SwiftUI gives us. This is why it's efficient. And understanding this is very important if you want to learn about SwiftUI performance. How it compares the nested structs, I don't know. But one thing it will do, it will loop over the properties. And it will, in this case, there's just the one properties, and it will see is it the same string before and after. And so if you put other stuff in there, like closures, they cannot always be compared, and so the body of your views might be executed more often than you think, which also might not be a problem, but it's something to be aware of. And let's have a look at what happens if we actually use like a dynamic value on line 18 here. So we change hello world to total, and now it's dynamic. And if we change the hydration, it makes that node dirty, it re-executes the body and everything else below it, and also the nested struct, and that is now different from before. And SwiftUI needs to re-execute the body of nested and recreate that text. And so another way to think of it is that SwiftUI always recreates the body of the nested views and always runs that, unless it can prove that it was the same value. That's at least my mental model there. And now we're going to take a slight detour and understand something, and that will help us understand why SwiftUI is the way it is. We're going to go back to our static site builder. So we have a function here, static site, and actually my first static site was in Ruby. My website, I wrote it with middleman, and it became really slow over time. And so I moved to Swift, and my code looked a little bit like this. It just took like 30 seconds to generate, which was too much. And so as I wrote it in Swift, it became much quicker. So here we write index.html, we create a blog, and in the blog function, we read all the files from the current directory, we loop over that with a for loop, and then we read the content for a specific file, and we write that content, turn the markdown into HTML, and we're good. And so we can step through this. If we now run that site, it generates the 3 files. If we change something inside 1.md, it generates the 3 files. If we add another file, it generates 4 files now, right? And so this was way more efficient than my Ruby version. It only took a few seconds to generate my site, right? Like, this is much nicer, but it's not incremental, and that's maybe a problem, right? Like, I noticed at some point as I was making edits to my blog post and changing images and other stuff, I really wanted to just have instant feedback and not wait 3 seconds. That can really slow you down at some point. And so I wanted to make this incremental, and it's actually not possible to make this incremental, because how would the for loop know, for example, if a file got added? Like, how would you do that? Like, how could you implement this in such a way that that would be incremental and only execute the for body for the newly added file? And so we can actually learn from SwiftUI, and we can turn these functions into structs. So we can say struct Here we go. Struct static site. Of course, this doesn't compile. We need to wrap these statements in a body. And so write some rule, and then we need to capitalize everything because we're dealing with values. Oh yeah, we need this body as well. Now capitalize the write and the blog. We can capitalize readdir. And this is actually interesting. I don't know if it was too quick, but you could see that the readdir is now indented, right? The body of readdir. And that is actually the dependency right there. So we now, every time files changes, we want to re-execute readdir and run the body of that. Same for the for loop. So we can take inspiration from SwiftUI and replace it with a for each. We can do the read file in the same way so that the write file now depends on that. We can write it with a capital W. And then there's some unnecessary nice things we could do. For example, if we want to store our blog posts in the blog post directory, we could do that. If we want to remove the parentheses on line 11 because they hurt now, that's much better. We can also make index.html the default output and write stuff like this and use like the environment to pass in the directory and all of that. So it starts to look a lot like SwiftUI, right? And there's a reason for that. So, oh yeah, we need to remove this index.html here as well. So this looks a lot like SwiftUI, and I built this incremental generator. We can step over the tree it builds on the right. So here we have the static site with two nodes, the write and the blog node. And if we expand the blog node, there's a readdir inside with two files. If we expand that, there's a for each inside, of course. And for each of these two things, it generates a subtree, right? So a read file and a write file. And this works surprisingly well. So let's look at an example. If we were to modify 2.md, this system here, this blog static site generator, actually only reads 2.md and writes 2.md, and it will not do anything else. If we were to add a new file, it would run the readdir. That triggers an invalidation of the for each, and then it just adds that node there. So it's super efficient. I was blown away. I wrote all of this. Let me say more. It supports the static site generator, supports everything that SwiftUI has. It supports preferences, it supports the state system, it supports the environment, everything. It's fully compatible, and I wrote it in less than a day. And we'll talk about how. So before we actually look at how I did that, we're going to do one more example. Oh, I went too fast. And look at a technique called defunctionalization, and that's essential to how SwiftUI works. So we're going to create an example that I took from the point-free people, a counter with decrement and increment buttons. And the problem with this content view here is that it's not testable. Everything that SwiftUI is really hard to test, so you want to move as much stuff out of SwiftUI as possible to make it testable. So our first thing we could do is wrap these closures or change these closures to functions. That's a little bit better, so we can make a decrement and an increment function and call those. A little bit better, but not really. But we can test it slightly better. What's much better is actually to create a model struct here. So we're going to create a counter model. We're going to store the value in there and have the increment and decrement methods. So the content view part doesn't compile yet, but the counter model is really easy to test. We can change our content view now to have that model. It's a little bit more typing, but we have a lot more testability, and it's very, very worth it. What the point-free people did is they pushed this idea of reducers a lot, right? And that comes, I think, from Elm and from React or Redux. And they say that it's even more testable. And you can actually mechanically go from a model to a reducer. It's just a mechanical thing. And what you do is you replace your functions with values. The problem is that we cannot really test which function gets called or which function that button calls. We can only observe the changes in the model, but we can compare values. We cannot compare functions, we can compare values. So that's what they did, and they actually, for each of these two methods here, they create an action. And again, this technique is called defunctionalization, replacing your functions with values. So you create an action for each of the methods, and then instead of having those methods, you have a single reduce, or I called it apply. You switch over the actions, and you execute the thing. And so now that's our model. and it's a reducer. And you can now call those methods. And what's really nice about this is that you get even more testability. For example, you could write a wrapper around a model with exactly the same interface that logs the actions. You can store your initial value and all the actions, and a list of all the actions that got called, and you can step through the entire history. So this gives you a lot of testability, and it's a completely mechanical transformation. And we could not really compare which functions got called, but we can totally compare an action, right? Like, that's equatable. If we wanted to serialize things, we could make this codable, and we can store that to disk. And so you can do this for any functional program or any function. You can defunctionalize it by changing your functions to values, making that refactoring, and all of a sudden you can store your functions to disk. You can compare them. And this is actually what SwiftUI does. When we saw that nested view, it's a value, right? It's a struct. In my mind, I read a function there, a defunctionalized function that builds up that view. But because SwiftUI cannot compare functions, or Swift cannot compare functions, they changed it to a view struct so that it can make it incremental and compare and see if it's the same value before and after. And this technique of defunctionalization, I would think that more than half of the people in the audience have used this without knowing it. And so I wanted to give it a name. I did not give that name because it already existed, but it's something to really think about. Like, when did you do this? When did you replace your functions with values? I'll talk with Nick. There's Nick. He did this without knowing this, right? Like, it's a very common technique, and I think by giving it a name and talking about it, we see maybe even more use cases of this. It's everywhere. So let's go to the last slide. So the reason why I said I'm really sure that it's completely compatible and why I was able to write this in a single day is actually the only bits that I wrote is read dir, read file, and write. And the rest is actually SwiftUI. So I built a static site generator on top of SwiftUI, which is a horrible idea. You know, never do that. Who wants a static site generator that depends on SwiftUI? But it works really well. I got full incrementalness. The first time it takes a while to build the site, but then my changes are instant. And the other thing, of course, that I wanted to show there is that SwiftUI is a build system. It's exactly the same thing. SwiftUI, spreadsheets, make files, packages, Swift compiler, it's all the same thing. You give it a description of what you want, and it turns that into an incremental system. That's all I wanted to say. Thank you, and I'm very happy to take questions here or afterwards. Thank you.